Linear programming is a mathematical modeling technique used to determine a level of operational activity in order to achieve an object. Mathematical programming is used to find the best or optimal solution to a problem that requires a decision or set of decisions about how best to use a set of limited resources to achieve a state goal of objectives. Why is it called linear programming? One of the areas of mathematics which is extensive use in combinational optimization is called linear programming. It derives its name from the fact that the linear programming problem is an optimization problem in which the objective function and all the constraints are linears. Linear programming was developed as a discipline in the 1940s. Motivated initially by the need to solve a complex planning problems in wartime operation. Its development accelerated rapidly in the post-war period as many industries found valuable uses for linear programming. It started in 1947 when George D. Danzig designed the simplex method for solving a linear programming formulation of U.S. Air Force planning problem. Soon became clear that a surprisingly wide range of apparently unrelated problems in the production management could be staged in linear programming terms and solved by the simplex method. George D. Danzig was an Air Force mathematician who worked on logistic problems. During the 1940s, and the Army needed a way to plan expenditures and returns in order to reduce costs and increase losses for the enemy. George D. Danzig is the founder of the simplex method of linear programming. Here's some example video for you to be able to understand more about linear programming of George D. Danzig.
So this video is going to be about Danzig's simplex algorithm, an algorithm for solving linear programming problems. Linear programming is optimizing linear functions subject to some linear inequalities. That's a lot of use of the word linear, so to get everyone on the same page, any expression of variables is called linear if none of the variables are raised to any exponent other than 1 or 0. For example, we might have the linear function 3x plus 5y plus 4z, and we may want to find the smallest values for x, y, and z, such that the following inequalities are also true for our values. This function is always referred to as the objective function, and the inequalities are called constraints. So that's linear programming in a nutshell, but in order to do the simplex algorithm, we need our linear programs to be what's called standard form. So the standard form of linear programs is to have an objective function that looks like this, and a set of inequalities that look like this. Now these may seem overly mathematical and complicated, but they're actually saying something fairly simple. The objective function has n variables, and they're denoted with a subscript value from 1 to n. Similarly, in the objective function, each of these variables has a coefficient denoted by c with a subscript value from 1 to n. This means the objective function simply can be any linear combination of the n variables. The inequalities seem slightly more complicated, but what the expression is really saying is that there are m inequalities, and each has the form of the sum of some variables with some coefficients similar to the objective function, and that expression is less than or equal to some other constant. So really it's saying things that we already kind of knew, just in a different, more concise mathematical way. The last expression is to simply state that all the values of x sub j have to be positive, which is called a non-negativity constraint. Right, so now we have our linear program in standard form, we can start to do the stuff relevant to the actual algorithm. The first step is to translate the information from the standard form into what's called slack form. Now this may feel like we're just sort of juggling around between different forms of the same thing, but to explain the motivation behind this, we first have to consider how this algorithm works in the broadest of sense. So to start with, consider a collection of lines on a two-dimensional plane. These lines represent the boundaries of the inequalities of a linear program in two variables. This is basically just your standard y equals mx plus c sort of thing. I've just taken the inequalities and plotted the variables against each other. So if we had an objective function of x and y constrained by these inequalities, then the solution would have to be somewhere within the region of R. Now, say the aim was to maximize an objective function that was just equal to y for the sake of demonstration. If we pretend that we can't see where on the graph this is, and we just chose a random intersection between the lines, we can see that we can move to nearby vertices to find a more optimal solution. Then, once we can't go any higher, we've obviously reached a local optima. So, going back to slack form, we'd start by introducing m new variables, which I'm going to refer to collectively as the slack variables and individually as y sub I. So each slack variable is associated with an inequality from the standard form, and is defined as the difference between the two sides of said inequality. This means two things. Firstly, if we plug the slack variables back into the original inequalities, we can see that our complex expressions reduce down to a set of non-negativity constraints over the slack variables, which will make the information easier to deal with algebraically. Secondly, if we set the values for our original variables to 0, we can obtain a solution to the system, from which we can start traversing towards the optimal solution. This is called the basic feasible solution. The last point to make about slack form is we also introduce a new variable for the objective function. We will refer to all of these new variables as the basic variables and all of the original variables as the non-basic variables. Right, so now let's get on to how to actually do the algorithm. Let's take an example linear program where we're maximizing this objective function under these constraints. As you can see, this problem is already in standard form, so now we have to convert it into slack form. So the variables on the left hand side of the equations are the basic variables, whilst the ones on the right are the non-basic variables. Now if we set all our non-basics to 0, we can find our basic feasible solution. Our goal is to increase the value of the objective function, so we notice that this can only be done by increasing the x sub 1 term, as it's the only positive term currently available. In general, if there are multiple positive variables, then any one of them can be chosen, as all paths will lead to the optimum solution. We need to increase x sub 1 as much as possible, but keep in mind the non-negativity constraints on all the variables. So we find the maximum value for x sub 1 in equation 1, which is 3, in equation 4, which is 4, and we also find that it's unbounded in equation 3. We choose the tightest possible bound so that all the non-negativity constraints are upheld. We take the appropriate equation and we rearrange it for x sub 1. If we then substitute this value of x sub 1 into the other equations, we get a new set of simultaneous equations. So now the basic values are x sub 1, y sub 2, and y sub 3, and our non-basic variables are x sub 2 and y sub 1. This process is called pivoting. The previously non-basic variable x sub 1 is called the entering variable, and the previously basic variable y sub 1 is called the leaving variable. So the first thing we do is find the feasible solution again, and with the new objective function we can see that the x sub 2 term is positive, so we're going to try and maximize it. Plugging in the feasible solution, rearranging and substituting back into our slack variable's non-negativity constraints, we find that in equation 2 x sub 2 is unbounded, in 3 it's bounded by 6, and in 4 it's bounded by a half. We again choose the equation which gives the tightest bound, which in this case is equation 4 with a half, and rearrange it for x sub 2. Then we again substitute back into the system of equations. This time we notice that the new objective function has no variables with negative coefficients, which means we can no longer maximize. So we compute the feasible solution, and this gives us our final solution. In this case we have x sub 1 is equal to 7 over 2, x sub 2 is equal to 1 over 2, y sub 1 is equal to 0, y sub 2 is equal to 11 over 2, and y sub 3 is equal to 0. If we plug these values into our objective function, we then find that the maximum value we can get is 25 over 2. That should give a reasonable intuition as to how the algorithm operates. The last thing to consider is the time complexity. If we recall, the algorithm works by traversing the vertices to find the local optimum. The worst case is when that vertex is reached after the algorithm has gone through all the other vertices. Unfortunately, the number of vertices in an n-dimensional cube does not rise polynomially. In fact, there are O of 2 to the n vertices. So, in the worst case, if we were to traverse all of these vertices, that would take O of 2 to the n. However, the worst case complexity is pretty unlikely in real-world uses. Generally, we don't have to traverse all the vertices. In practice, simplex tends to compute in polynomial time. But there is no such algorithm that actually has a worst case polynomial time.
Thank you so much everyone for listening on my discussion about the history of linear programming. I am hoping that you have learned. Bye bye.